My name's Matt, and this is LIV Mixed Reality. If you want to be a big cop in a small town, then maybe you should f*** up the model village. But if you want to be an appropriately sized Steve, seen from a considerable distance, then keep watching and I'll show you how. So in this video we'll go through several ways of being able to show either more context for what you're doing in a scene or more detail by moving and zooming the camera. Timestamps, as ever, are down the bottom, so if there's a section you want to focus on, then jump to it. We'll start off with some more of the simple techniques to zoom the camera in and out, and move on to some of the more complex operations. There's a few different implementations of mixed reality, and some of the techniques I'll show here will only be possible in some of the implementations. I'll put up on screen a graphic for each technique and which implementation it's possible to use it in. The different implementations I'll cover are LIV version 1.5 for titles like Superhot or Virtuoso, LIV enable version 1, which is games like Hot Dogs, Horseshoes and Hand Grenades, Virtual Tracker like Balls Cricket, Virtual Controller for really old games like Job Simulator and The Lab, and finally games which require a physical tracker like Vivecraft or Vacation Simulator. The first one is possibly the easiest, as it's something that can be achieved by any game that is directly LIV supported. As a note, some games also directly monitor the external camera.cfg file, and this might be possible in some manually composited titles, but you'll need to check on a game-by-game basis. Balls Cricket is an example I'll show you which is able to do this. Finally, you would be able to do this in a non-automated way for other games, but you'll need the exotic maths as shown in the final section to make that work. With that out of the way, let's get to it. When editing a camera in LIV, you may have noticed the FOV override section. This allows you to change the end result field of view that is output by LIV. Entering a number of degrees in here will set the output to that FOV. Simple. You can just set that when you start your game to get a wider or narrower field of view. But it's also an option that can be automated by what are called URI commands. I've put a link in the description to the documentation on this where you can find out about all of the options available, but we'll just focus on the FOV override. To use this, we'll need to compose the right URI and then send that URI to LIV. On screen now is the documentation about how to do this. So to set the FOV to 90 degrees, we replace the number at the end of this with 90. Now we need to send this URI to LIV. I use Streamer.bot for my automation. I highly recommend it if you've got the time to set it up, but any other way of getting the system to run a command will work too. If you've got some software that's able to just invoke the URI, then you're all set. Otherwise, and also for testing purposes, I use the window command start to invoke the URI as follows. Start, two double quotes, because the start function for some reason needs a window title, and then the URI we've composed, also in quotes. If we run this from the command line, we get our FOV set to the required value, effectively zooming in or out. If you're doing this from an action in Streamer.bot, or probably any other software to run this, you'll likely need to run the command prompt first. The command we've just generated will need to be passed to CMD as arguments. In Streamer.bot, run a command, find command, which is in Windows System 32, and then put the command in from before. Wrap that whole thing in quotes and then put a /C followed by a space at the start. This is great as there's no loss of quality of the virtual environment. Zooming in is great, as is zooming out, but at larger fields of view we start to get a fisheye effect which might not be desirable. Another limitation on this is that because we've got to do the round trip via command line, we can only do about one action per second. If there was a direct API that allowed for this to be called dozens of times per second, it would be possible to do a smoother zoom, but this is something we'd have to ask LIV nicely for. If zooming in using the FOV shifting on LIV is not a valid option for you, then there is the much more obvious and straightforward way of just scaling the output image directly. I do this by creating an additional scene in OBS with the required transformation and switching to it. The downside with this approach is that because you're scaling the output image, you lose quality. Simply changing the field of view may not be enough of a solution to get the scene you want. Depending on the game you're playing, you may want the camera to be further away. This can avoid the fisheye effects, but also can include more of the foreground in the scene. For example, the normal convention for sports games, such as this cricket game, isn't to be filmed right up in the batsman's face, but rather to be filmed from the boundary and zoomed in. The end fight on Minecraft is difficult to see from this close distance, but much easier to see the dragon perching when the camera's further away. We can move the camera by using OpenVR Input Emulator. To do this manually, click Device Offsets, tick Enable Offsets, and in the Driver from Head Offset section, you can add a positive offset to the Z axis. Helpfully, we can use the command line to automate this. As well as moving the virtual camera, we will also need to manually scale the physical camera to match. This is where maths comes in. Yep, maths. This is where my video retention falls off a cliff. Bye guys! For those of you who are staying, it's maths time. It's basically high school calculus, but I know that will put a bunch of people off. I've created a Google sheet that you can take a copy of to do the calculations, and I'll go through what the calculations are trying to achieve here. If you want to skip the reasoning behind this, just jump to the next timestamp. The total FOV of a camera might look a bit like this, but we can split it in two so that we're working with right angle triangles. We therefore need to halve the FOV. The way I learned at school, which might give some of you flashbacks, is soccer TOA. Now, we need TOA because that's tangent with opposite and adjacent. Handily, the LIV virtual camera is lined up exactly to its own local Z axis. So, let's substitute adjacent for Z and opposite for X in our diagram here. It's important here that the value for Z we use is reasonably accurate, so make sure that you measure from the camera to the point where you typically stand in your play space. This method also relies on not moving too far from this distance that you've measured. So knowing how far we are from the camera will tell us what the frustum width at that distance is. Now, when we increase the distance to the camera, we can work out what the additional width is and the ratio between them. Once we've got our ratio, we just need to take our camera dimensions and multiply each of the dimensions by the ratio. It doesn't matter that we only use half the FOV, as the ratio will obviously be the same. If you're using LIV Composite, you'll need to scale the camera input. I do this by capturing in a separate instance of OBS and passing it through the OBS virtual camera. Having separate scenes here allows me to automate switching between different scalings. If you're manually compositing, you can just create a scene for each ratio you need and then switch between them as appropriate. Now that we have both elements that we need, it's time to put them together to automate this. You'll need to simultaneously switch the scene to scale the physical camera input and move the virtual camera. The physical camera part can be achieved by whatever stream automation you normally use to switch camera scenes, and automating the virtual camera via OpenVR Input Emulator needs two things to happen. When using OpenVR Input Emulator on the command line, we'll need to pass both the position that we want the camera to move to, but also which device number it is. Let's get the device number by calling the client command line utility with the argument list devices. In my instance, the virtual tracker is ID 3 and the virtual controller is ID 4. For all games that use the virtual controller method of tracking, you'll want to use the ID for the virtual controller. For everything else, you'll need the virtual tracker ID. This ID will change depending on the order you start up your controllers and trackers in, so you will likely need to get the ID for the track devices you want to manipulate each time you start SteamVR. There's going to be loads of ways that you can achieve this in your setup, so you can work out the way that works best for you. For reference, I use the execute C# code function to get the device ID into a variable that I can use for the entire session. I've added links to the code that I use to achieve this on GitHub in the description below, if that can be of use for you. Putting it all together, we need to run client command line with the device offset argument, the device number, and set the driver position offset with 0, 0, and then the Z offset. This time the unit is in meters, which is considerably more sensible. Additionally, to tick the enable offsets function, we run the same command again, but with the argument for device offset, the device number, and then simply enable. One of the examples earlier was about televised sports having cameras at the edge of the pitch but then zooming in again. This requires us to combine both moving the camera backwards and also changing the field of view to zoom in. Relying on LIV to do the FOV manipulation here results in a blocky image as the physical camera feed is scaled down and then up again. To negate this, we'll need to do both the FOV scaling and the movement scaling manually, which should result in an image which is only scaled once and therefore be the highest possible quality. Again, I've put the calculations in the Google Sheet for you, so you can just use that. Essentially, we're just using the same maths, but this time also adjusting the angle theta when calculating our ratio. Okay, so that's all the tricks I know. I hope that's been useful for you. If it has and you think it will be useful for other people, give us a like and hopefully that will help others find it. Subscribe for more like this and leave a comment if there's other tricks you think will help others too. Thanks for watching and see you next time.